Hello, friend. Welcome. In this video, we're going to continue our discussion of how traps and system calls are handled in the XV6 operating system. So this particular video, we're going to be looking at the mechanisms, what happens when a trap or a system call occurs when we're running in user mode, so when a regular user program is executing. All right, so we're going to actually get into and look at the code of the trap handler, the user vector, the user trap handler, and those kinds of things in this video. So if you're ready, let's go ahead and get started. So XV6 handles traps differently depending on whether the trap occurs while executing in kernel mode or in user mode. Okay, so in this video, we'll concentrate first on, actually, it's a little bit maybe the more complicated case, but what happens when one of these traps occurs when a normal user program is running and we're in the less privileged user mode. Okay, so I won't. So reminder, a trap can occur for any of the three reasons. The program could explicitly in software make a system call by using the eCall instruction. It might do something illegal, like try to access an address that is marked only to be able to be accessed if you're in supervisor mode or something like that. So access an illegal address is a common thing, or if a device interrupt occurs. Okay, so I won't go over kind of the hardware mechanisms again, but so for all three of those reasons, the hardware will do its thing that we talked about in the previous video to save the current state of the program counter and then to set the program counter to the value in the STVec. So that causes this sequence to happen here. So the saved the trap vector address is set. The program counter is set to whatever is in STVec at the end of the hardware mechanisms, among other things. So that causes to start executing code specified by the operating system. For XV6, STVec is going to be set to the address of uservec, which is in which is actually the trampoline page. So this is in the trampoline .s RISC-V assembly code if you look in the kernel module here, which we'll look at in a second. So basically that trampoline page it saves all the registers into the trap frame. So I just wanted to jump back to a figure from the previous chapter and the previous lectures that we talked about. So when we were talking about the process of address space, talking about page tables, remember that at the top of the virtual address space, in the page, when we set up the page table for a process, we map the trampoline page and the trap frame. Okay, so remember, also another thing to remember when we're looking at the code here is that there's actually only one trampoline page, and this actually has code in it. So this is the place where the trap vector, the uservec, is loaded into, that does the initial save of the state. And every process maps to the same trampoline page, as well as if we look at the kernel space, also maps the same trampoline page at the same address, right? So that's part of how XV6, since that's exactly the same address, whether we have a kernel page table, or if I can go back to the user page table, user page table, it's actually at the same address. So things will still keep working when we switch from the user page table virtual address space to the kernel page table versus virtual address space, and back in the other direction as well when we're returning from this. Okay, and the other thing, this is only in the user address space, so it's not in the kernel, but each process has a trap frame. These aren't shared, but that is actually going to be the location where the registers get saved into memory when the trap starts, and they get restored from when we're ready to return back from kernel space to the user process that was interrupted. So let's start by looking at the trampoline page that has the uservec address, which is the start of the trap handler routine that XV6 uses. So the code for the trampoline page is in the trampoline.s in the x86's kernel. So if we look at this, you'll see that there's a label for the address. This is the address that's actually put into the STVEC. So if we go back and look at the boot code, somewhere in there, it's going to be setting STVEC to be this, so that whenever traps occur in the hardware, it will actually jump to this. And also, as I just finished mentioning, this page is mapped to the same virtual address location in all page tables, user page tables and the kernel page table. So jumping to that address will always go to the same code. So as a reminder, the hardware, when a trap occurs, the hardware has done the stuff that we described in the previous video, including near the end, is that it set the program counter to whatever was in the ST so whatever's in the STVEC register, which will be the address of this label here, uservec, the program counter gets set to that, and we're starting to execute from here. All right. So the first problem that we have, we need to save the state. Okay. So and by the way, the STVEC is only set to this when we're in user mode. So when we get into kernel mode, another thing you'll see here is that so if a trap happens from kernel mode, we'll actually trap to somewhere else. So you should also remember that interrupts are turned off by the hardware at this point. And we're not going to call a system call. So the only thing that could occur here before we change over to the kernel trap handler is if we made an illegal call. So we just have to be careful that we never, try to access a legal bit of memory or something before we get to that point where we've changed it over to going to a different place if an exception or a trap occurs. Right? So it shouldn't be possible. Right? But first of all, before we can do that, we have to save the state. So remember, we mentioned the scratch. We need at least one free register in order to do all these here. But we don't have one unless we free one up. Okay, and don't ask me why. I'm not certain. I guess we can't just use scratch directly, so we do have to free up one of the registers. So at whatever value happened to be in A0 that the user program might have been using before it got interrupted or trapped, we jump to here, we just save that in the scratch register. That's what's happening here. So each process has a separate trap frame. So notice basically the base address of the trap frame is being done here. So all these is doing is saving each of these registers to a particular offset on the trap frame. A couple things to note about this. So notice it skips 8 addresses each time here because each register holds 64 bits or 8 bytes. Right, so that's how we do this. Another thing, if you count this up, there's only 30 here, but we also save A0 to an offset of 8, so there's 31. There's actually 32 general purpose registers in RISC-V, which I wasn't certain why, but I wasn't certain why there seemed to be only 31 being saved here. It turns out one of the registers always holds the value 0, which is kind of something that's unique to RISC-V as far as I know compared to other computer architectures. So a lot of code, machine code, was always using 0 a lot, so you'd always have to put 0 into a register before you could use it, so that saves it. So there's always one. If you look at the RISC-V description, there's one register that just always holds the value 0 in it. So yeah, if you look at this trap frame, so the constant for this is defined in mem layout. I don't remember if we mentioned this when we've looked at mem layout before. So notice it's just at where the location of the trampoline is minus the page size. So it's just below that. Okay. But also the same thing if you look in the process.h header file, there's a structure called trap frame, which so besides the A0 register and other stuff, a few other things can actually be saved on this trap frame as well. But within the process structure itself, so another way the trap frame values can be accessed is if we have the process structure, the process entry, we can get whatever saved on the trap frame through there. So that's used sometimes as well. So after all the registers are saved on the trap frame, we're actually setting up some things here. So we're actually taking some other stuff out of the trap frame. So for example, we're basically switching over to the kernel stack pointer and the kernel page table here, among other stuff that happens, right? So here, this pulls out, so the kernel stack pointer is actually kept on the, every process has a separate kernel stack, which is separate from the user stack. So this gets pulled out, becomes the new stack pointer at this point. As well as the page tables. This is where we actually switch from the user page table to the kernel page table. Okay, but again, this stuff all works here before we do the switch because every process maps this trap frame to the same virtual address, including the kernel page table. Right. So even after we do the switch, we're fetching and executing from the same virtual address space, no matter whether we're using a user page table or a kernel page table. So once we're done with saving the state here in the user vector on the trampoline page, we're actually going to jump, called the user trap. This is C code. So the purpose of the user trap is to determine how to handle what caused the trap. So it's going to have to figure out whether it was a system call, an interrupt, or an exception, and do the right thing to handle whatever it is. So here, I skipped over it, but another thing that's actually in each process's trap frame is the location of the user trap. So the kernel trap field in there, or the thing that's offset 16 from the top of the frame, holds the location. So by putting this into T0, that is what we will jump to. So this will effectively do a system, call, as if we're calling a function. So this is jumped to the address that's on here. And I believe at this point then we're using like C function call. So it'll be using the whatever on the stack pointer to push and pop parameters on there and stuff like that. So here at this point, user trap is defined in trap.c. Just find user trap here. So this is C code at this point that's being executed. Yeah, actually the first thing it does is if we remember that SPP, this is checking the SPP flag in the status register. So if this doesn't indicate that the trap came from user mode, there's a panic. So we're not supposed to actually be running this procedure if we weren't in user mode when the trap occurred. Something bad went wrong. In general, whenever a panic happens, it means that we're at some state or some location that should never be possible unless some corruption or a bug has happened. But the first thing the textbook talks about is this here. So notice up to this point, the STVec, which is the location where the trap vector, so the location if another trap occurs that we should jump to, was to the trampoline page that we were just looking at, right? So interrupts had been disabled, but it could be possible that a system call or an exception occurs. But basically all the code at this point is careful not to do a system call, and if an exception occurs, that would have caused it to jump back to the trampoline page. So, that has to be checked. But at this point, we're going to change it. So this will be the next video of what happens if a trap occurs when we're in kernel mode. And so this is basically changing it. So traps or exceptions after this will go to a different, this kernel vector page instead of the trampoline uservec page. So this call here can basically determine what the actual current running process was on the CPU core that this code is executing in. So once we have that, we can use its trap frame to do other stuff here. Because you know, again, we're using the kernel's page table, but these will be pointing to the correct place. So this will be actually pointing to the place, the individual trap frame for the process. So this code should work to do assignment. So here, you know, the program counter that we need to restore is set here because now if another trap or something happens, that will get overwritten. So we actually have to remember this and restore this when we are transitioning from kernel mode back to user mode. So that gets saved over here into the saved program counter. So this next part is basically like a switch statement, or you know, it's basically checking whether the trap was from a system call, a device interrupt, or an exception. Like for system call, so here notice that the return PC that was saved is actually pointing, if an eCall happens, is actually still pointing to the eCall instruction itself. So when we return back, we want to actually return to the instruction after that, right? So RISC-V instructions all are exactly 32 bits because it's a RISC architecture. One thing that RISC architectures usually do is it makes certain that all instructions are regular, like the same size, for example. Right? So since all are 32 bits, we can figure out what the next instruction is going to be. It's going to be 4 past that eCall instruction. So 4 bytes or 32 bits past that will be the instruction we actually want to return to and start fetching and executing from when we return from kernel mode to user mode. So device interrupts were actually disabled by the hardware, you know, not system calls or exceptions, but device interrupts were. So XB6 allows for nested device interrupts. So if we're currently working on a device interrupt, but another one occurs while we're working on it, that's fine because we've already changed where the traps or the interrupts will go. They'll go to the kernel vector, the kernel trap vector now. So we can turn interrupts back on. So if we get other device interrupts while we're still handling this interrupt or this system call, we can handle those in the kernel vector. And then, let's jump to the syscall here. We'll quickly, I'll save that for a bit here, but this actually determines which system call was called by the user program and executes that code. So, otherwise, if it's a device interrupt, so this function, if we went and looked at it, will determine if it's a device interrupt, and it will return a non-zero value. But it'll actually handle it as well. So if it figures out it was a device interrupt, it'll actually handle it and return a non-zero value. And that would be all that happened. We would determine that it wasn't a system call, but it was instead of a device interrupt. So if it wasn't a system call or a device interrupt, it must have been some kind of an exception. So we're doing things to, again, if the cause was one of these in the scause register, it might have been a page fault. We do some lazy allocation. Otherwise, basically, if it's not an exception that we try and handle, everything else gets done down here. So basically, we kill the process. So again, if we're accessing memory that's illegal for the process, it would actually end up down here. You'll get a strange message, but that's where this is coming from. Kill the process. So before we look at system calls, let's look at returning back to user space. Okay, so if we successfully handle the system call or the interrupt, or we handled the exception instead of, if we kill things off, we actually exit here and don't do a prepare return. But if we are going to return back to user space, the first step is this. This is still in the trap.c. So if we look at prepare return, we're doing we're reversing some of the stuff that we did before. So we're basically going to change the STVec register back to the trampoline page, back to the uservec. Right. So we don't. Again, we're going to be careful. We're not going to call system calls. So we're not going to do an eCall. We're going to be careful not to cause any other kind of exception. But we don't want device interrupts. We can't keep those from happening. So we need to turn off device interrupts for a bit here, because if we do this before, if an interrupt occurred before we set these things back up, it might go to the trampoline page before we're ready for it, or it might go to the kernel page before we've actually done this call here. So this call here will switch it so that the next trap will go again to the trampoline page, which should only be coming from uservec, from when a trap occurs when we're running user mode. Okay. So if you remember, on the trampoline page, we actually changed to the kernel page table and the kernel stack by getting those out of the ptrap frame. So now we're ensuring again, putting those back in there. So we want to know what the top of the kernel stack is right now, and what the kernel page table is. So again, we can switch to those the next time a trap occurs from user mode. Okay. And here, remember, if you don't, the final thing I'll mention here on the prepare return is, what's happening here is it's possible that other interrupts or traps occurred. So the EPC might not be what it was when we switched from user mode to kernel mode. So we actually set the SEPC to the program counter we saved, because now when we return from this, and when we perform the sreturn instruction, that is what will be the program counter that gets set back, so that we continue from where the trap occurred back in the user mode program. So then we return from the prepare return, so we're back to the user trap code that we were looking at. Right? So the last thing that we do is we don't quite yet, but we're preparing to switch back to the user table. Right? So this actually, the return value from this function is the user page table, and that gets returned in register A0. So when you return something by default from C code, it actually sets A0 to be that value on return. So this return here, basically, remember, back to the trampoline page, basically we jumped to the user trap with this instruction. So on return, it actually continues from this part on here. So the code on the trampoline page has both the code to transition from user to supervisor mode, and then when we're done, we're doing the reverse. So the user return is transitioning from the kernel mode back into user mode. Okay, so a lot of this is the reverse we did before. So we have to restore all of our registers from the trap frame. Yeah, so there's not too much that happens here. And then the final thing is that sreturn call. So that, because, again, going back to here, because we, I skipped over. So here we're actually switching to the user page table. I should have mentioned that. So remember, the A0 on return holds the address of the user page table. So that actually switches back to the virtual address space of our user program that we're going to do. And then, the sreturn, that was set up back on the trap C here. Actually, trap C in the prepare return. So, the last thing the prepare return did was to set the SEPC register to the saved program counter that was on the trap frame. Okay. So the result is, at this point, EPC has the actual program counter that should be set by the sreturn. So this causes those hardware actions that we talked about to be reversed, right? So this will among other things, will change the program counter to be whatever's in the EPC, the SEPC, the saved program counter. The effect of which will be that we will continue executing from the instruction after where the trap occurred. Okay, so before we leave this video, this topic, let's go back and look at a little bit more detail of what happens if a system call was what caused the trampoline page to be changed to and to change from user mode into kernel mode to handle a system call. So if you look, the user programs call library functions in order to make system calls. So for example, let's look at the usys.s, which is a user program. I'm sorry, let's look at a user program that calls write. So whenever a system call is made, there's a function in userland. There's actually some assembly code in userland, which is what this will end up calling. Right? So the write system call, just to remind you, basically the first one is the file descriptor, the second one is the string we want to write to that file descriptor, and the third one is the link. So the number of bytes in the string that should be going, sending as output to the file descriptor that we have. So as our textbook did, let's look at the shell.c program in user space. Right? So let's go down to user space and find sh.c, because shell.c, that's the thing that that is run by the init process, basically. So it gives a simple shell, asks for you to type in commands on the shell, and executes them. So basically in the main function, it calls the get command. Now, the basic thing on the get command is it first just writes out a prompt. So the shell prompt is just a $sign with a space. So there's this write system call here. So here's where these .asm files are not actually compiled. These are the result of the compilation, but in a little bit more of a human readable form. So if you open this up and look for the get command, you can kind of see how each line of C code got compiled into RISC-V code here. So basically, when you call a system call like write, and so this last one here is actually going to invoke, this is going to do a long jump to, I think, to something. So the effect should be that it ends up doing a long jump to the assembly code that's a hook to the write system call. So we'll go to that in a second here. But before it does this, up to some number of parameters are going to need to be put into A0, A1, A2, A3, up to 6 or 7. If you have more parameters than that, you have to do something more complicated. But we've only got 3 parameters here. So the first parameter, the file descriptor, should go into A0. So I think that the C code did a little bit of optimization here. So since both the first and third parameters were 2, it put a 2 into A2, which is what we need for A2. That's the number of characters to write out. But then it also just copied 2 into A0. So we end up with 2 in A2 and also 2 in A0 from these 2 instructions. And then this other one, I won't go into details, but it's setting up A1 to be the pointer to this string constant that we want to write out. So when we want to invoke a system call, there's another thing still in user space that actually has the eCall instruction, right? So this is the thing that you can link with in user space to use the system calls here. So if you look at the usys.s and we find the write here, like it's shown in the textbook, this is all that happens. So that jump long goes here. We've already set A0, A1, and A2. Whenever you do an eCall, A7 is the register. A7 should have the system call that you want to invoke. So this is just a integer value. So yeah, all these come from syscall.h in the kernel. These definitions for the values for sysfork, sysexit, syswrite. So if we look at syscall.h in kernel space, Um, there it is. So it's a simple header file, right? So the exit is basically use the system call number. Or sorry, the write that we're looking at is using system call number 16, right? So that's the value that actually ends up in the A7 register. And A0, 1, 2 have the values that the write system call should use. Okay? So let's go back to the usertrap function. So remember, we looked at this. In particular, we said that if it determines that the trap was caused by a system call, and it does that by looking at the scause register here. So if it's a system call, it ends up calling the syscall function. And that function is in syscall.c. Okay? So notice, here, the values of A0, A1, A2, the registers could have been changed. So we don't know what's in those actual registers anymore, because we could have gotten interrupted by another device interrupt and done some other things. We might have changed those registers ourselves by doing some of this code here. So if you look at syscall, and if you look at the system call functions in general, they're not going to be using the registers. They're going to expect that they can access the saved values of the registers as they were when the eCall instruction was invoked in the trap frame, right? So the only thing that system call does is it looks up the system call number that was in the syscall.h. Get these both together here. So in A7 should be one of these values, right? So we're pulling that out of the trap frame saved version of the A7 register. And then here we've got a table of function pointers. So that number just acts as an index to actually call the correct system call function. And another thing that you should know, this is discussed in the textbook, is that on return from a system call, the return result code or return value is saved in register A0 to be returned back to the user process. So whatever the system call returns gets put into the trap frames A0, and then when we switch back from kernel mode, back from supervisor mode back to user mode, this gets restored, right? So this wouldn't have been the same A0 when we called the system call, but this will be the result of the system call function that gets returned back to user land, right? So I'll admit I'm not familiar with the syntax here, but looking at this, this must directly be specifying that so there doesn't seem to be any value at index 0, but this must guarantee that the value at index 16 on this array is just the function pointer, like syswrite. Okay, so this syntax here is really just calling whatever we look up from that table, this function pointer. Right? So if you look at syswrite, we jump to syswrite. I guess that's in a file called sysfile.c. So I guess these are the system calls having to do with the file system, read, write, dupe, and stuff like that. Right? So anyway, this is the actual stuff that happens on the syswrite here. I won't go into the details of these things, but you can see that there's these things that will be able to grab something that's expected to be a file descriptor argument or an integer argument or an address argument. So basically the 0th argument, the one in trap frame A0, should have been a file descriptor. So that this, if we go and look at this, must be looking in the trap frame to find the A0 value and then interpret that as a open file descriptor. The argument 1 should have been an A1, and that was just a pointer to the string to write out, and then 2 was the number of bytes in the string. So an integer at argument 2 gets put in. One final quick thing I wanted to mention. So whenever a system call returns, by convention in XV6, it returns -1 if an error occurs. So right, if we have problems, if that file descriptor isn't valid, it returns -1 here. But like if you look at file write, if you look at what it returns here, it's probably easiest to understand this. So it has an integer that's going to be the return code. So basically, the file write is if it successfully if you ask it to write 2 bytes and it successfully writes 2 bytes, we ask it to write in bytes. The number we actually wrote was I here. So if that's equal, it returns the number of bytes it wrote, right? So a positive value or 0 usually means success. And for write, it's only successful if it successfully writes the number of bytes you ask it to write. If it didn't write in the number of bytes you asked to write, it returns -1 here to indicate there was some kind of error. It didn't complete everything on the write. All right, so that's it for this video, where we talked about how traps are handled when the trap occurs in user space, and we're transitioning from user space to supervisor mode. So from user mode to supervisor mode. So XV6 actually handles traps differently depending on whether we were currently in user mode or kernel mode. So the next video we'll talk about what happens when a trap or an exception occurs when we're in kernel mode. When we're in user mode, we start by entering the uservec. So a register is set up, the stvec register is set up with the location of the trampoline page that has the user vector, which is basically the assembly code that should be first executed when a trap occurs when we were in user mode, when that trap occurred. Okay, so it's good to understand that trampoline page, the uservec, and the user return are mapped to the same virtual address, both in all user page tables and the kernel page tables. So that makes it easy to switch from the user page table to the kernel page table, and everything still keeps working in terms of executing instructions in the program counter and things. Basically, the uservec, that assembly code that first gets executed, saves the state. So it saves the state of all the registers and things for the process that was interrupted into the trap frame. And each process has its own individual trap frame. Of course, that has to be the case, because you can't have 2 processes sharing a trap frame. 2 processes are in interrupted state. They need to have their own save of the registers and things when they were in that state. So the uservec ends up calling the usertrap C function. So that routine is what actually handles the actual trap. So it does do some things like reenable interrupts, and this is where we switch to the kernel stack and the kernel page table. And then, there can be 3 kinds of traps. So it could have been a system call that caused it, or an exception, or a device interrupt. So basically it figures out which one of those it was, and it does the right thing to handle the trap. On return, it calls prepare return, which sets up the process to do the reverse of these things. So, it switches back to the process page table and the stack, and then it jumps back to the user return, which is back to assembly code, and that's the thing that actually restores the registers from the trap frame. And then the final thing is it calls the S return, which is going to restore the program counter so that the next fetch execute is happening from where the user process was interrupted. Okay? So when a system call is invoked, the eCall instruction, it basically from software causes the hardwired trap mechanism to occur. Right, so this is what causes the user program to be able to request that we switch to supervisor mode and have the kernel perform an action for us, like a write system call, whatever a system call it needs to have perform. So in general, the parameters that are input to a system call go in registers A0, A1, A2. You can only have like 5 or 6 of these. If there's more, you have to do something more complicated. The A7 register is loaded with the index of the system call to perform. So the user trap function called system call, that is really just a lookup So it uses an array of function pointers to figure out the actual function to call, and it ends up invoking that. So it uses the value in A7, which is actually not in register A7 anymore. In syscall, it has to look that up in the trap frame. So the value that was saved for register A7 by the process in the trap frame. And then just in general, be aware that the convention is that 0 or positive values for XV6 mean a success, and a -1 is usually returned to indicate an error. And so the return result from eCall is returned in the A0 register, although again the system call the system call functions will return it in A0, but this function actually has to put it into the trap frame first, so that when we're restoring all those registers from the trap frame, A0 gets restored with the return result from the system call. Okay, so that's it for this video. As usual, I hope these things are useful for you for understanding how operating systems in general work, and in detail how XV6 works. If you have any questions, let me know. But I hope to see you then in the next video.